Welcome to video 2 of my series on how to perform FM modulation and demodulation using the Python programming language. Last time, we learned that it was possible to encode information by varying the frequency of a sinusoid. In this video, we are going to take the concepts covered last time and apply them towards an actual computer simulation that will make those concepts come alive. First, before getting too far ahead of ourselves, we need to collect the tools so we can actually do the work. The first tool that we are going to be getting is called Anaconda. If you would like to see how to get Anaconda for yourself, just follow along. So here I'm just heading over to Anaconda's website where I can download the software. Of course, I've dropped a link in the description below this video so you can get over there easily. They actually have different versions of the software depending on what operating system you are using. Since I am in Windows, I will download the Windows version of the software. As I had mentioned back in the introductory video, we will be working with the Python 2 programming language. This is why we will be downloading the Anaconda suite that includes Python 2. What is really handy is that Anaconda includes matplotlib as well. Now that Anaconda has been downloaded, it is time to install it. While installing, just go with all the default settings. Just keep in mind that Anaconda may take 15 minutes to install, which is something that I've purposely not portrayed in this video. Now I did go ahead and unselect these checkboxes. The reason being is because I didn't want to be redirected to some web page. Now that the installation has completed, click on the Windows Start menu, and from there, scroll down to the Anaconda 2 folder, where you will find some bundled applications. For our interests, we will be using Spider. From here, we can actually implement the concepts from video 1. So, here it goes. The first thing I want to do is provide the file that we will be saving the code to an actual name. Of course, I want to save it as a Python file. As for the name, I will call it FM Simulate. So, now that we are finally going to write some code, you'll see that Python is really easy to read. First, we need to import matplotlib. Matplotlib includes a special module called PyLab. PyLab powers Python with MATLAB-like functionality. Since we now have our tools ready for a simulation, it is time to set up a table of values. The reason being that the values under the x column will eventually power our equations. As you may remember from high school math, each value descending down the list of x values must be incremented by a consistent value. In the field of digital signal processing, this is called a sampling period. We must keep the sampling period small enough to give the graphs that we will be plotting a decent resolution. Now that we have set on what the resolution of our simulation will be, it's good practice to provide a descriptive comment for anyone that would want to refer back to this code at a later date. Any line that starts with a number sign will not affect your code. It is now time to finish defining the x-axis for the table of values. Let's call it TS, where T is for time and S is for sample. From now on, each value in a table will be referred to as a sample. Python by itself does not have the ability to build a table of values in an easy-to-use manner. This is why we will call on matplotlib's PyLab via the alias we set up earlier. Calling upon PyLab via its alias will provide us a drop-down list of all of PyLab's functions. We will be calling upon PyLab's arrange function to set up the x values for our table. This is how the arrange function works. First, you provide what you want the first value to be. I've chosen 0. Afterwards, you pick a value that the largest value in the column can never be equal to or greater than. As for each value or sample in between, it will be incremented by whatever the sampling period is equal to. It is now time to write out the equation that represents the location of the slider from the first video. The equation will take each sample held in the TS column and then calculate the corresponding Y sample for the adjacent column. What is great about using PyLab is that it allows us to write out equations almost like you would on paper. Keep in mind that whenever you want to refer to the sine function or the mathematical constant pi, you will have to refer to PyLab via its alias that we set up earlier to do so. Now that we've inputted our equation, we have a completed table of values that can be graphed. Graphing with PyLab works like this. First, type out PyLab's alias, and then select the plot option from the drop-down list. Inside the brackets, provide the time values first, followed by the Y samples. For the plot to be drawn to the screen, you will need to type out PyLab's alias again, but this time, select the show function. After running this code, you will notice that we produced this graph from video 1. Let's take the concepts that we have just learned and apply them towards making the graph that was at the bottom of the screen capture a reality. The first thing I am going to do is to write out the equation in Python of the modulated signal from video 1. So just for the sake of making this easy to follow, I have gone ahead and highlighted each part of the equation as I have typed. While I'm typing this out, I should also mention that we can reuse the time values stored in TS for each new equation. The last thing I need to do is assign values to both the center frequency and the modulation factor. For now, I set the modulation factor to 15, the only reason being that it forces the signal stored in YM to have a really visible effect on how much the carrier's frequency varies. Alright, let's swap out YM from the plotting function with YC. Let's see what that looks like. For the reasons that were explained in video 1, you will notice that the frequency of the modulated signal varies from low to high, as it should. If you try the examples in this video, I will say congratulations, you have successfully simulated FM modulation. In video 3, I will be visiting how to demodulate the signal YC.